All right, so up until now, we've done a lot of descriptive analyses. And once again, what is a descriptive analysis? That is when we're looking at something and trying to figure out what has happened or what is happening now. So let's talk a little bit about what a diagnostic analysis is. So a diagnostic analysis is performed to investigate the underlying reasons why something happened. And it's stuff that typically you can't just look at descriptive data and figure out what's going on. So we have to do some kind of other thing. And so basically diagnostic analyses can be broken up into two broad categories, and the first one is that whole identifying anomalies and outliers. And this is one thing I can't do on the board. Correct spelling. So outliers and anomalies. So once again, what is an anomaly? And this is the one thing that we're going to keep coming back to. So an anomaly is something that departs from what is expected. So in many ways, an outlier is similar to an anomaly, because an outlier is just an observation or a data point that lies outside of the expected distribution. And outliers, can be mistakes, or they can be a result of fraud, or it could just be what it is. So there's a lot of overlap between anomalies and outliers. And so basically, to detect an anomaly or an outlier, it is important to establish the norm or the expectation. And depending on, if you were in marketing, you'd expect that the increase of sales that your company has is going to be roughly equivalent to other companies in the same industry. And so an anomaly would be, well, our company's sales grew twice the rate of our competitors. And so then you want to come up with what's the explanation for that anomaly. Maybe our new products were selling really well. Maybe the other competitors' products were going out of phase. If you're looking at accounting, you expect all the accounting records are going to be in conformity with generally accepted accounting principles, or GAAP. And then, PwC goes in, finds its clients not doing the right thing. They capitalized rather than expensing R&D equipment, which is not the way you do things in GAAP. And so that's something to go take a look at. Or if you want to look at finance, our company's bond prices are priced just below the U.S. government treasury yields, and then all of a sudden our company's bond price fell in relation to the U.S. government treasury yields. Why did that happen? What are some of the causes? It could be, well, maybe our company's been having poor financial performance, and so our bonds were graded a little bit riskier, thus lowering the price. But these are all anomalies. They're different than the norm. They deviate from what is expected, and so you have to do some kind of diagnostic analysis to figure out what's going on. And a lot of times there's not one size fits all. This is what you're going to be you're going to investigate, you're going to be looking at things. So what else would you do with a diagnostic analysis? So diagnostic analysis is all about finding previously unknown linkages, patterns, and relationships. Between variables. And so this is things where you do like drill down analysis. And this is really like the kind of thing we're doing. We're playing with pivot tables, and you start doing filtering, and you start looking at different rows and columns and whatnot. And then the other thing would just be performing higher end statistical analyses. All right, so, these are some examples of things that are going on. And actually, right now, we're going to talk about a way of identifying anomalies, and it's a neat little rule or neat little law that pops up, especially a lot in fraud fraud investigations. So, what are we going to talk about? We are going to talk about. Let's get another couple lines here. Benford's law. So, what is Benford's law? It's also known as the first digit law. And what it is a really weird statistical phenomenon that describes the distribution of leading digits in real-life data sets. So what does Benford's law say? Well, it says the first digit of a number is more likely to be small than large. So specifically, the digit 1 should occur around 30.1% of the time, as opposed to the digit 9, which is expected to appear about 4.6% of the time. So it's a really intriguing phenomenon. The law is named after the American physicist and mathematician Frank Benford. He first observed this pattern in 1938, and he initially discovered it while he was studying tables of logarithms and other statistical data sets. And then later on, it was found that this phenomenon applies to a wide range of naturally occurring data sets, like financial data, population numbers, physical constants, even the lengths of rivers in countries. So the implications of Benford's law in business analytics are significant, and they have some practical applications for detecting anomalies, and specifically for detecting fraud, because fraud would be an anomaly. So when you analyze financial data sets or other numerical data sets, the deviations, any deviations from the expected distribution of Benford's law, could be any number of things, but typically errors or discrepancies or fraud. And so if the data doesn't follow this distribution, it suggests that the data could be manipulated, or somebody just got lazy and not recorded it the way they should. For example, if we were doing accounting, Benford's law can be used to detect irregularities in the accounting records. So if certain financial transactions or figures have an unexpected distribution of first digits, it would probably trigger further investigation into whether the data is accurate or reliable. And so this application of Benford's law is used a lot in forensic accounting and auditing to identify potential frauds. So this is a pretty big kind of thing. So what is the expected probability distribution for this? Let me give you a chart here. And so this is our distribution. So the first digit of 1 should occur about 30% of the time, 2, 17, 3, 12, all the way down to 9, which should be about 4.56% of the time. And so how do we use something like this to determine fraud? Let me throw up a graph here that has plotted some data against Benford's law. So if I had something like this graph here, you can see the blue bars are the percentage that the first digit appears, and then this orange line would be the data that we've plotted from Benford's law. And if I was looking at something like this, this seems a bit off, because the digit number 1 is way less than what Benford predicts, while 6 itself is way more. So in this case, I would look at this data set and go, hey, there might be something going wrong with this. This could be fraud. This could just be errors. Now, I've got a couple of caveats. So a few little things that we should know about it. And we got three big ones. The first one is bigger is better. So Benford's law works better with larger data sets. So while the law has been shown to hold true for data sets for as few as like 50 or 100 numbers, you probably want more than 500 data points to be suited for this kind of analysis. The second thing with Benford's law we have to worry about is we need what's called equal opportunity. So equal opportunity is to conform to the law. The data set must have an equal chance for numbers 1 to 9 to pop up. So let's look at the NBA and heights of NBA players. Shortest NBA player that's played was Muggsy Bogues from 87 to 2001. He was 5'3", and the tallest were 7'7", and I'm going to murder these names: Monte Bol and Jorge Merasan. They played during the 70s and 80s, but they were 7'7". NBA heights would not be an example of equal opportunity because 1, 2, 3, 4, 8, and 9 have no chance to be the first number. So therefore, this would not work for them. Something else, like a web hosting company that only charges its customers either $49.99 or $79.99 would be unsuitable because the numbers 4 and 7 are the only ones that would pop up, so there isn't an equal opportunity for each of those to happen. And so, for the very last one, we have, well, there's no definitive proof for this. And truthfully, coming from a science background, having this called Benford's law rubs me the wrong way because it's not a law, it's a theory. But the Benford's law calculation, it can't definitely prove or disprove anything. It's something to look at. So some CPAs have attempted to establish mathematical thresholds by using z-score calculations. Remember, we talked about that a couple days ago, to definitively measure and interpret the law calculation, but these really don't make the law any more or less accurate. They merely help lessen the subjective interpretation of whether or not a chart adheres to Benford's law. And so really, when you're looking at it, just a simple visual examination of a chart is really all it takes to raise questions on whether or not there's concerns with the data. If the chart isn't following closely Benford's curve, then consideration should be given to scrutinizing the data a little bit more closely.